Hi, my name is Kevin Kiningham. I'm presenting Kessel, a flexible low-power accelerator for cryptography. So just to start off, let me explain what I mean by an accelerator. So in a typical IoT device, you usually have fixed function circuits that will accelerate particular computations that get used over and over again. So an example of this would be many operations in cryptography. For example, a Bluetooth chip may have a fixed function accelerator for AES-128 if you're transmitting encrypted packets over Bluetooth consistently. One downside of these accelerators, as they usually are implemented today, is that they tend to be very fixed function. So for example, your AES-128 accelerator can't implement RSA, it's not going to implement DES, it's not going to implement anything other than the AES-128. So why bother with flexible accelerators? And the main reason is that you may not be able to predict over the long term exactly which ciphers that you're going to want to be able to use. So security requirements tend to change over time. New ciphers come out. Maybe you want, for efficiency reasons or for just legacy reasons or protocol reasons, you may want to upgrade or change whatever your cipher you're using. Hopefully AES-128 doesn't get broken, but if it does, you'll want to push out an update that will change whatever cipher you use. And if that happens, you don't want to have to go out and replace all the different pieces of hardware that are existing in the field. There may be millions of different devices. People predict, billions or tens of billions of IoT devices will soon be deployed. And, having somebody go out and try to replace each one of those devices when they may be embedded in physical objects or inside of a bridge or spread over huge geographic locations may be infeasible. You'd really like to be able to just put up a software update and still retain the advantages of having these accelerators. Additionally, you'd like to be able to deploy your system in multiple countries or multiple different regions that have different regulations on crypto systems. So for example, China and Russia have different laws about what kind of ciphers can be deployed in silicon, and they also have what kind of ciphers you can actually use in your product. So if you want to build one specific product, you would prefer, instead of having to spin a different chip for each different country that you're deploying in or a different region, you would have one particular chip and then each one would have a software update that you could use. So why not just use software? After all, software tends to be fairly flexible. It's pretty much every IoT device out there will probably have some sort of microcontroller in it. And the answer is that it tends to be fairly inefficient. There's a reason why a lot of these IoT devices have these fixed function accelerators in them, and that's because without the sort of specific circuit that can implement these or accelerate cryptography, you end up spending quite a bit of energy on just encrypting and decrypting things. So an example application that I actually had used for an application here at Stanford, we basically did read from a thermistor 20 times, encrypted it, and then sent it over a Bluetooth connection. And it turns out if you did this AES encrypt in software on our particular device, it actually represented almost 20% of the total energy consumption of the device. That's a pretty large energy consumption. Obviously, if your phone had 20% less battery life, or you had to go and change the battery of some device 20% more often, you might go out and buy a competitor product. So what we would really like is the efficiency of the hardware and the flexibility of being able to change and do different ciphers. So that's what our research is focused on, and we came up with Kessel, which is an architecture specifically designed to try to be flexible, accelerate a broad set of ciphers, but do so in a way that's reasonably flexible. And the actual architecture we settled on was this sort of 32-lane 8-bit SIMD architecture. And the reason really that we settled on this was because we went through a very large number of ciphers, symmetric ciphers, asymmetric ciphers, sort of different stream ciphers, sort of different implementations that people had done. And we found that most ciphers have an extremely high amount of internal parallelism. And there's a couple different reasons for this. One is that people, when they design these ciphers, tend to try to take advantage of sort of existing hardware that's already out there. And in particular, one piece of hardware that in in most CPUs and sort of desktops that's really fast and energy efficient is sort of these vector coprocessors or vector instructions that you can use. Intel SSC or Neon would be an example of this. And so cipher designers actually have for a while been specifically designing their ciphers to be taking advantage of this sort of parallel hardware. It turns out that a lot of implementations already sort of use this sort of design, and it would be nice to tailor our architecture to be able to take advantage of this sort of intrinsic design pattern across many different ciphers. So the actual architecture is split up into two pieces. One is the front end part, and the other one is the back end. The front end is basically the part that takes the instructions from memory, it decodes them, and then actually pushes the control signals to the back end. And the one interesting part about this front-end architecture is that there's actually no data-dependent control flow. And the reason this is interesting is because if you actually look at a lot of these implementations of different ciphers, they tend to try to very strongly avoid data-dependent control flow because of timing attacks. In particular, variable timing is a very common way to leak information about different keys. And so because of that, many practical implementations try very hard to not use data-dependent control flow. Additionally, not having data-dependent control flow actually significantly simplifies the design of this accelerator. And as we'll see later, it actually contributes a significant amount of energy savings to the overall design. Unfortunately, one of the reasons why you would like to have data-dependent control flow is looping. So the pretty common pattern in sort of block ciphers, or actually many ciphers, is to have rounds of a specific function. And so unless you want to repeat your code over and over again, usually you'd like to use a loop for that. But it turns out you actually don't really need data-dependent control flow if all you're doing is a fixed size loop. And you can actually use what's called a loop stack, which basically at the beginning of the loop, you save the pointer for the first instruction of the loop, and at the end of the loop, you check to see how many times you've executed this loop, and you either go back to the beginning or you go to the end. But you never actually need to look at the data that's being executed in the cipher. So the second part of the architecture was the back end. And if you remember, the back end was made up of 32 SIMD lanes. So each one of these lanes has several components. The first part is the register file. So the way the instruction is actually executed is you read something from the register file, two values from the register file. You either execute a crossbar, interlink crossbar, or you execute an ALU operation, and that gets stored into an accumulator register. And the next cycle, the accumulator register can either be added to one of the lane before you, or you can just store the accumulator back into the register file. So the reason for this particular layout is that we really want to be able to do sort of big number operations in our SIMD architecture. And that's really useful for things like ECC and RSA, basically many asymmetric ciphers that operate on large integers. So this sort of accumulator setup actually lets us implement sort of large word, 1,000-bit word adds or multiplies or whatever in a way that's reasonably efficient. Additionally, we've added some extra ALU operations specialized for cryptography. So these aren't usually specialized for any particular application, but they are specialized for sort of the whole domain of cryptography. And in particular, I wanted to point out two particular instructions that were important. The first one is carryless multiply, which happens to be an instruction that's pretty easy to implement in hardware, but not usually added to most CPUs. But it does happen to be used in a fair number of ciphers. So AES would be an example, some modes of block ciphers, and also some other stream ciphers use carryless multiplies. Additionally, when we actually looked at the sort of instruction distribution of different ciphers, we found that it was very common to do some sort of arithmetic operation followed by a bit operation. So usually this would be something like an add followed by a shift, or an add followed by something like an XOR. So we actually made it so that you can compress an add followed by one of these bit operations, or an arithmetic operation followed by one of these bit operations, into a single instruction. And so finally, the last major component is this inner lane crossbar. So the inner lane crossbar allows you to broadcast the value from a single lane to all the other lanes, or it allows you to perform a permutation or a shuffling of the different lane values. And this turns out to be very useful since quite a few ciphers end up using sort of either permutations or they end up using this sort of broadcasting operation. In software, in non-SIMD architectures, this actually tends to be quite hard. You have to do some like masking operations followed by maybe a shift, followed by another masking operation, followed by a store. In our architecture, you can do it in one single cycle, and it's nice and fast. Additionally, this crossbar operation, we actually built in the ability to do bit slicing, which is a sort of implementation technique where you can sort of permute the bits of different values across different lanes. And I'll touch on this a little bit more. So we took this design and we implemented it in Verilog and synthesized it for 100 nanometers. And we performed power analysis through simulation. So we also rewrote a bunch of different ciphers to try to take advantage of the architecture. And it turns out, as we had previously said, there are actually quite a few implementations that already take advantage of this sort of SIMD idea. Additionally, we used these bit slicing techniques to remove S boxes. And so when I was talking about before about how you can, about bit slicing to do permutations, there's a whole sort of rich literature on being able to use bit slicing to using bit slicing instead of doing lookups. Additionally, we made very heavy use of this permutation network, so it turned out to be very advantageous to include it. So this is our evaluation on AES 128, and we compared across an ASIC, our design, and then 2 RISC-V designs. So our design used this bit slice implementation, and then the RISC-V column is basically a naive AES 128 implementation, and then the RISC-V bit slice implementation is basically taking the same cipher that we ran on Kessel and running it sort of on RISC-V. And if you notice, kind of keeping the actual cipher implementation constant, we end up getting a very large improvement in energy, about 60x. If we instead use this sort of the naive implementation, we end up getting about a 10x improvement. So the disadvantage of the naive implementation is that it's not side channel resistant. It doesn't have like a lot of these extra features that you would want in a real practical implementation. So we are significantly behind the ASIC, but since we basically remove about a 10x improvement of power over the RISC-V, it actually ends up not mattering too much because we end up moving cryptography from the range of like 12% or 15% of power overall usage to about 1% or 2%. So we could definitely improve it more, but it's I think roughly in the ballpark. So the actual energy savings, where it comes from, if you notice, it actually came from the number one place it came from was from the faster execution. So interestingly, RISC-V takes about 4.5 cycles, at least this implementation of RISC-V takes about 4.5 cycles per instruction, and our architecture takes about 1 cycle per instruction. And so this actually has quite a bit to do with the fact that there's no data-dependent control flow. The RISC-V architecture is small, doesn't really have a branch prediction unit, and so it ends up executing lots of instructions that don't need to be executed simply because it goes down the wrong path of branches, or it ends up waiting for values to be computed. Whereas our architecture, since there's no data-dependent control flow, we never mispredict a branch. We never wait on values. And so because of that, we end up having far fewer cycles per actual instruction. Additionally, we also use fewer instructions overall, and this is mostly due to the parallel nature of SIMD. We're able to take advantage of the inherent parallelism in many ciphers, and we also are able to take advantage of the specialized operations that we have in our architecture. So this about 10x power savings over the naive implementation means that we're able to take the original example to about 1 or 2% of overall power consumption instead of maybe about 17%. So in conclusion, hopefully I've motivated the fact that future crypto accelerators need some sort of flexibility. And we think that Kessel can provide this sort of flexibility and while still being efficient. The savings comes from a number of places, but overall it comes to about a 10x improvement, at least on AES. So we're working hard on evaluating on a much wider range of ops, and currently we're still implementing them. So That's it. Thank you.
So you mentioned power side channels, but won't the use of the crossbar reveal power usage that depends on the key?
Yeah. So that's a good point. So the use of the crossbar can reveal certain things about the key. So you can be careful. It depends. I mean, we haven't evaluated it for power analysis yet, but that is definitely on our future work.
Hi.
Oh, where are you? Oh, there you are. You're right in the light. I can't see you very well.
How do you think this would compare against like a RISC-V processor with an actual pipeline and maybe instruction set extensions like MAC to help it handle big nums?
Gotcha. So basically, unless you include a pretty good branch prediction unit, adding extra pipeline stages doesn't necessarily help you. So the thing that we found was that you end up taking a lot of different branches and then not being able to predict them super well. You could, of course, spend more area, spend more power to do branch prediction, but you tend to try to reduce the amount of power as much as possible in these sort of low power systems. In terms of adding extra instructions, there actually is some literature on adding different instructions to various different architectures. The problem is that just adding one single instruction doesn't necessarily cover a lot of different things. So for example, the permutation network that we had, that wouldn't necessarily be a single instruction, or it'd be difficult to do in a single instruction. There's also other operations. You need to add a lot more, basically, instructions in order to try to get this. And yeah, it'd be something to compare, but I don't think it would be that good. So. Yeah, sorry, this is with a 3-stage pipeline. Yeah, that's right. It was supposed to be equivalent to about a Cortex M0. That was their advertisement.
Any other questions? Great, well, let's thank Kevin again.
Oh, one more.
We got one more. Sorry.
Okay, one last question. I was intrigued by the S boxes. You said you are using the permutation network to implement that, or?
So we use basically bit slicing to get rid of the S boxes. So it's a little bit complicated. I can talk about it afterwards. But basically the idea is you can kind of permute the bits across different lanes, and then sort of since with an S box, you're actually applying a function to each individual byte, and the function that gets applied is the same, you can kind of convert that table into sort of a circuit, and then make the circuit into instructions. It's a little bit complicated. I can talk about it.
I think I understand it. You can use the permutation network somehow to implement a table lookup.
Well, we use the permutation network to do the bit slicing, and then afterwards we do the sort of circuit that would implement in just normal instructions.
Thanks.
Okay.
Cool, so thanks, Kevin.
Thank you.